we go. Okay, there we go. So I'm going to talk about comms and compute co-design because we as in my team at Intel, I'm not going to speak for all of Intel, although I hope they're on board, we think this is going to be a really big part of 6G. And the reason for that is that, as you all know, there is a huge trend of clients using more and more apps concurrently. And at the same time, the apps continue to increase in the richness of the content that they're supposed to provide. And that obviously requires greater compute capability. And the problem is nowadays, it's often at lower latency requirements and on energy limited clients. I mean, if you think about some of the kind of clients we have today, like robots in a factory, they have far less compute than, the old standard laptop. So offloading some of that compute burden is going to be very important. But the question then is, which jobs do you offload and where do you offload them to? And in that question, you have to consider the job requirements, and that is obviously the compute burden. So, how many operations is this function going to take? The offload size, which is not just the input, but the output, and that's where a lot of the trickiness comes in, because sometimes you don't know what the output size is going to be. Then there's, of course, the time budget and the job interdependencies, because often we want to split up a job into subtasks, but it's not as simple as just splitting and then doing them in parallel. There's often a lot of dependencies. And then, of course, you have to consider how much compute capacity do you have on your client and the current and predicted load, because while you may be able to ascertain the current compute load on the client, while your job is being computed, new compute jobs might come in, and depending on the way that your client, or in this case also your edge or your cloud, handle new jobs, you could find that what you predicted based on the current load is nothing like what you actually get. And then, of course, if you're talking offload, you have to talk about the transport speed. So how long is it going to take to send the input to the edge and get the output back from the edge or the cloud, whichever it is that you choose? And this entire problem is what we call comms and compute co-design, or if we're really lucky, co-optimization. Assuming we could actually solve this problem, the other issue here is that solving it requires inputs, and the estimates of those inputs are actually really, really hard to ascertain. So things like determining the time that a job is going to take to compute, this is not an easy task. And then figuring out how much time that would actually take to compute on the edge and every possible compute location in the network. That is a lot of benchmarking, if in fact that's what you decide that you're going to need to do. And then just determining the input and output transport speeds. We have been estimating channel quality forever, for my entire lifetime in wireless, but it's still not an easy thing to do, especially when you overlay different types of transport protocols. I mean, estimating TCP is a very different animal from UDP. And then we've got other things now like QUIC and a whole host of things. So these things are not easy to estimate because often they're not published. Like in that sense, I'm talking about compute estimates of various functions in an app, or they're constantly changing, or both. So basically our research is not just about developing this optimization protocol, but it's helping to develop the ecosystem. Because ideally, we would like an ecosystem that starts to provide some of this information, maybe some of the benchmarks, maybe app developers start to provide the benchmarks, at least based on some baseline CPU and memory size, something like that. So it's a very, very large research space. And if you compare it to the wireless space, it's very new. If you look at the literature, the bulk of literature comes in the last 3 years. So there's a lot of work to be done here, and really, primarily my talk, the purpose of it, is to lure you in. So I wanted to give you just a quick picture of a sample comms and compute architecture. Just because I'm a visual learner, I don't know about others, but it helps me at least to consume the idea. Now, this is just an example of a private network. It's obviously not gonna, it could actually apply to a public network too, but there are things missing here. Like, for example, I have one edge cloud node. And in reality, we are potentially going to have that multiplied by n, right? Especially if you're looking at the cloud. You could have a horde of potential compute locations that you have to consider. But you know, when we started looking at this, we thought, oh, okay, we're going to look at an enterprise environment, and let's pretend, for the sake of argument, that we have a really huge server room, one server room. Even that is not a simple problem. Because, you know, if you look at it, you know, on the right you have that server room, let's say, and then on the left you have in these yellow boxes a bunch of cells, and they're each served by an AP/base station, and they serve a bunch of clients, and in these clients there are a bunch of apps. So every point here, every text bubble here is a knob in the optimization problem, and this is why it is so difficult. Because so you start in the app here, and the first thing you have to do is split the job, or maybe not split the job, but that's one of the decisions you have to make. And then once you know, split the jobs, now you've got to decide where are you actually going to compute this. Is it going to get computed on the client, or is it going to get offloaded? And if it gets computed on the client, how are you going to compute that? Are you going to just do some simple processor sharing, or are you going to do something more intelligent? Then if you actually decide to offload, how are you going to offload that? Just the scheduling of that is a complicated issue, because now you could have some intelligent scheduling of your TCP flows, if you know that's what you actually happen to have. And you have to remember, it's not just scheduling among the compute flows, it's scheduling among the compute and all the other data flows that you have. How are you going to prioritize that? You still have real-time traffic. That has nothing to do with compute. Then, once you actually do decide which TCP flow gets the first access to the channel, you've got to figure out, based on which radio access choice you have, which also is a decision that you have to make, and assign the TCP flows or whatever other flows you have to those specific radio access technologies. Now you've got to figure out the share of the channel use, right? I mean, you've got intra-client, you've got between the AP and you know, on the downstream, at least on Wi-Fi, when it's not, you know, time division, and it's just random access. Now, you know, you might actually want to boost up your AP's, you know, speed of access, simply because you really want to give it a chance to get those compute outputs back at the, you know, at a priority rate. Then once it gets up to the AP, I don't have it here because in a private network, it's all wireline, and so we really didn't feel like there was much impact from scheduling that uplink queue from the AP to the server room. But in reality, when you have hundreds and hundreds of nodes and it's an enormous network, that actually could be another knob that you have to play with. Then once you get actually to your chosen edge cloud server choice, you have to, again, decide on your compute scheduling. Is it going to be processor sharing, or are you going to do something smart? And then the same thing on the downstream. Do you do something intelligent on downstream? You certainly have to when you come to the AP. Once you get to that AP, you don't just want to be going round robin or something. You've got to pay attention to the deadlines. You might be getting really close to the deadline of that compute output. So you see, it is a really big problem. And now what I want to talk about, though, is, again, assuming you could figure out a very nice optimization solution for that problem, the biggest issue, and I'm going to talk about it in the next 2 slides, are actually determining the inputs to that optimization problem. And the biggest one that we face is just figuring out the compute estimate. I mean, how are you going to figure out whether or not to offload if you can't predict how long it's going to take to compute in these, you know, hundreds of potential locations? So the problem with that is determining compute time is really difficult, because it depends not only on your inputs, and the input, by the way, is not just your executable code and the metadata, you know, the libraries, it's the actual input. So, you know, I mean, granted, there are functions that don't have input. It's just like a runtime environment. You just go ahead and run it. It's the same every time. But there are other cases where, let's say you want to do video analytics. A 20-minute video is going to take far longer than a 2-minute video. And quite frankly, even a 2-minute video is going to take far longer if you say, no, 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 I need the accuracy to be up, 99% versus 50%. So that's a very difficult task. And as I mentioned earlier, the other problem is the output that gets returned. Sometimes you have no way of predicting the size of the output. So how then are you possibly going to predict the return time? And the other problem is that the time it takes to compute a task depends on how much time you're actually given on a core. So whether that's on the client or on some edge cloud server, how much time you can't assume you're going to get 100% of the time on the cores. So how are you going to figure out the time it's going to take if you don't know your allocation time? Especially when we're talking about the edge. I mean, at least the client could potentially decide, once I put you on my cores, I'm not going to split time no matter what other job comes in. But A, that's not always true. Sometimes you have, a processor sharing scenario, even as simple as that. You now have to somehow predict, okay, what's going to be coming while I'm processing this job? What kind of jobs are going to come in? So I can predict sort of your share. But especially if I'm the client and let's say the decision is on me, I mean, you could make this a centralized approach and, have a network provider actually make these decisions, or you could have a distributed approach where it's the client who always decides. But if that's true, how do I know what the edge node is going to give me? Even if the edge node tells me this is how loaded I am right now, I don't know what's coming. And I don't even know, if I don't specifically know the algorithm that the edge node is using, even if I could say, oh, load is really low and this is going to be stable, I don't know what the edge node is going to give me. So predicting time is very hard. And then, of course, your runtime depends on which CPU you have, the memory type you have. So the question then becomes, how do we do this? Are we going to benchmark every function and every input to every function on every possible compute node? That seems a little unrealistic. I mean, maybe not for functions that are used very, very often. Okay, fair enough, we could do that. But I don't see that being the case for every function. So how do we do this? And honestly, I think one of the most exciting and interesting research areas in this space really is determining functions that can actually do these translations. I mean, that would be such a win in this space. If I could say, I've benchmarked this task with this set of inputs on this CPU with this memory, and you could say, okay, well, I don't have that CPU, and I have a different memory, and the inputs are going to change, and I could actually interpolate or translate somehow into a compute estimate that, okay, it's not going to be perfect, but that could be, roughly accurate. That would be an enormous win. And that is an incredibly hard task. And there is work being done on this already. A lot of them are using ML techniques. So, for those of you who are in the ML space, I think this is a very exciting research area. And then finally, of course, the compute time itself depends on, again, how a node actually maps a job across the cores and time. And there, one might ask, first of all, how is it done today? In a lot of cases, we don't really understand. And the other question is, can we improve it, especially if you're a client device maker? This is something that one might actually want to consider, looking into now that we actually have very strict time limits on compute. But with regards to the actual optimization problem, the question becomes, could we maybe request guarantees from edge and cloud nodes, if need be? Or if the decision is being made, on the edge and cloud, and it's some kind of centralized optimization, can we ask for guarantees from the client? If I send this to you, if this gets computed on your node, can you guarantee that I'm going to get X amount of time over the next, whatever, milliseconds? So the other problem, or the other major problem, obviously, in determining compute offload, is the time it's going to take to transport the data. So again, like I said earlier, there's a huge amount of input data, and then you, of course, have your result, the compute result that, generally speaking, you want to get back. And the problem with estimating this is that the you need to know the size of the executable code, the metadata, the input data, and the output data. And as I said earlier, while we can measure the size of the input data, we often have no idea what size the output data is going to be. And then, you have to also consider caching opportunities. I mean, if it is true that some of this code could be cached, then you need to know whether or not it has been, or you're going to be wasting a whole host of time transmitting data that doesn't need to be transmitted, which could suck up your compute budget. And then, of course, as I said earlier, the choice of transport protocol makes a huge, huge difference. Some are easier to predict than others. Some have way more overhead than others. So that's a big factor. And then, of course, the flow scheduling, like I said earlier, how you actually prioritize flows, not just among, from compute to compute flow on a client and, on other nodes, but also between different types of data flows. And then, of course, there's the good old standard, the good put. What's the good put of the actual underlying radio access technology that you have? But in the end, the bottom line is we do not, even with best known methods, the estimates for transport time are really poor. And the fact of the matter is, if the error in those estimates is on par with the difference in compute time, it makes it nearly impossible to decide where to offload. I mean, obviously, if the variation in your transport estimate is from 5 to 10 milliseconds, but the delta between offloading and doing on the client is 100, that's a no-brainer. But what if they're really close? Or what if the transport time estimate varies from 1 second down to 10 milliseconds, which is what we've seen on our demo, on our POC? Then it's really hard, especially, as I said, because latency estimates, or not latency deadlines these days are so tight. So this becomes a really difficult problem. So in the next 2 slides, and I don't know how much, I have a few minutes left. I'm gonna skip my last slides, but I want to talk about 2 more things. These are not difficult to predict, but they are extremely important in the optimization problem itself. And the first is the subdividing of tasks. I mentioned it briefly before. But the bottom line is it obviously would be very attractive to be able to subdivide tasks, because then I can parallelize. The problem, though, is we often have interdependencies. This thing on the right is an example of a task that you could split into multiple subtasks, but you see that dependencies, the output from 4 has to go as input to 7, and the output from 2 and 3 have to go as input into 5. So you need to pay attention to not only how much time it takes to compute each of these little nodes, you also have to consider how much time it would take to transport the output from one as input to another, depending on where you actually decide to compute these. And the thing is, it's not, even if you said, okay, well, gee, let's look at number 5, okay, so it takes 2 and 3, I'm just going to make sure 2 and 3 finish at the same time. That's not necessarily what you want to do. What if 4 takes significantly longer than 5? Those are both inputs to 7. In that case, doing number 2 really quickly makes sense. It makes sense for 5 to have to wait on 3, because in the end, 4 and 5 might finish at the same time. I mean, it is a complicated scenario. And the other thing that is interesting about partitioning tasks is with some functions, it isn't so obvious where the best cut location is. Because, and I thank Gustavo and Agrim for this, they actually brought this to my attention. This is actually a neural network from a paper. And what the authors here are showing is that depending on your cut location in this neural network, the best location, if you're looking to minimize latency or minimize energy, is not necessarily the front or the end of this job. You might say, oh, well, the compute, on the edge is so fast. I'm definitely going to offload. But depending on where you cut, the amount of data that you have to offload and the time it takes to offload that could completely consume your savings of offloading. So it's really important to look at, the way in which the time to transport and the way in which the time for compute on the client node versus whatever edge node you're using, edge/cloud node, it's important to see how they vary, depending on where you actually cut. And this is a fairly complicated plot, and yet it's just a linear graph, right? I mean, this is not, there are no interdependencies here other than just one to the other. And still, it becomes a complicated issue. So that too is a very interesting research area. And finally, of course, there's caching on the edge in the cloud. Like I said earlier, if for functions that actually get run a lot, it makes a lot of sense to cache them. Because then, you know, in the end, all you'd need to do is actually offload the input and return the output. That's a huge savings. This is really attractive for things like streaming workloads, like in a factory, let's say, for example, right? How wonderful would it be if all the code that I need to actually run video analytics is already on the edge, and all I keep doing is, you know, sending pictures, like slices of video. It also allows logic with side effects to be offloaded. So, you know, one of the issues that sometimes we have is that when you run a function, it might change some variable. And that might not be the output, but it might change something in the environment. And if you know which those are and you can cache those, that becomes a very attractive thing. But in order to do this, you really need to start delving into this, you know, new networking paradigm, which is this named data networking. And I know, you know, at Intel, we're super interested in this space, and a lot of other companies are as well. And the attractive nature of that is that instead of having to track where things are located, you can actually, you know, call it out by its name, and you track it that way. So that, too, is a very important research area for this functionality. So I'm actually going to close here. I was going to talk about an interesting use case and then talk about Gustavo's research, but it's in the slides, so you guys can. Are you sure? Okay, well, people are, you know, don't blame me later. It's Jeff's. I will talk briefly about that. I am doing, I'm championing, as they call, research with Gustavo de Veciana. He's the one who introduced me, for those of you who don't know. I think most of you know him, though. I've actually done research with him on a lot of topics over the years. It's always fun. It's always challenging. I'm always impressed by what his students can actually do in, you know, a week's time. I always assign, you know, I always have issues and questions, and then I'm thinking, oh, I'll give them a month or so. And then the next meeting, they're like, okay, so we did that. So it's fun. But anyway, so the work that we're doing is actually on the optimization problem itself. So, you know, they're looking at it from an analytical point of view. And basically what they do is that they're looking at, you know, they're defining certain traffic sets of, you know, it's a job type, it's a client type. So let's say, you know, depending on your client type, you have different types of compute capacity. And the job type might have different cut locations, let's say. And then there's an average channel bit rate. And then they, you know, based on the estimated or the predicted input rate of those loads and the revenue you get from actually completing those computes at different cut locations, they have found that you can actually find an optimal allocation or an optimal admission control policy. But you know, the important questions that remain are things like, you know, how do we learn those offered traffic loads? Like, that becomes a really big deal because, you know, it may be, in fact, in factory settings, that's a very simple thing. In fact, I think this is a perfect solution for a factory setting where, you know, it is something like a robot that just takes a picture every single, you know, every 5 milliseconds or something. So in predictable spaces, that is totally doable. But what about in an enterprise environment? I mean, human beings are very unpredictable, right? So figuring out how to learn and predict offered traffic loads is very important for this solution. And then, you know, the big question there too is, you know, how can we actually go ahead and centralize this? Because you can't optimize without a centralized solution. Anything other than centralized is more of a co-design, not a co-optimization. And the question is, can you actually centralize this and do it in real time? That becomes a really big burden on communication, but it is something that we really would like to answer. So I'm going to end there. I hope I piqued your interest because it's an exciting area. And if I have, Gustavo's around to talk to if you're here at the university, or you can always just reach out to me. So thank you.